I am here to talk about how we moved from basically a Pig and Hive infrastructure to Spark at Netflix. So I just want to give a little context for what that means, like what do we actually do. So in the long ago, we were mostly a pig shop. We had some Hive jobs, but Hive didn't really give us an easy way to hook in to the right path, and that was primarily what we needed. I covered this in my last talk a little bit, but what we needed to do was guarantee atomicity for changes to our tables. Pig was really good for this because they actually had an API for plugging in new data sources and data syncs, and we primarily used Pig for that reason. We needed that because we're particularly sensitive to queries just lying to you. That just happens when you're running on S3 sometimes. Happens in HDFS too, but it's more common on S3. So we were very sensitive about that, and we've been very controlling of the right path in all of our big data products. The nice thing and the bad thing about Pig was that the pipelines required data engineering. Pig is not a language that I would recommend for basically anyone, because it nicely mixes this high level, oh, you can get so much done, with low level, you can't actually optimize it. It's pretty difficult to use. I actually don't understand Pig at all. I think I'm one of the lucky ones that have never had to actually learn it. But it still made our data engineers pretty productive. Like, they were really happy in a Pig land, and they weren't really all that interested in moving on. They had to understand the processing engine, but they were actually really good at that. And they could come up with pipelines that were, at least at first, on par in performance with Apache Spark in the 1.6 days. So it was pretty difficult to try and get them to move. Fast forward to today, this is a graph of all of the executions that happened on our clusters for a week ending Friday when I wrote these slides. So you can see that in terms of job executions, Spark was 92.5% of all of the executions that happened on our Hadoop clusters. Pig came in at 4.28%, and everything else was, less than 3%, around 3%. So this is a pretty dramatic change for 3 years worth of work. I should also point out that this is not in terms of MapReduce applications, Yarn applications. This is actually job executions. If we use the application measure, then Pig was a significantly larger chunk because it runs multiple applications for every Pig execution. So like anytime it needs to run a stage, it actually submits that as an application. In terms of cluster runtime, we still have, unfortunately, a pretty large chunk of Pig on our cluster at 14%, but we've gotten Hive down to less than 0.2%, so we've really come a long way. In terms of bytes read and bytes written, Spark also dominates 90% of bytes read, and this is S3, of course, and 80% of bytes written. So we've come a long way. So Spark is now greater than 90% of job executions, and to give more context to that, this is a big deal for us because we have Spark executions in the high tens of thousands every day. So this is a lot of jobs that had to move over, and really a huge long tail problem. And you can continue to see that long tail in the fact that we have so many Pig jobs, nearly 5% or like 15% of cluster runtime spent in Pig even today. So these are jobs where we just haven't touched them in a really long time, and they keep chugging along, and it's probably not worth the human time to move them over from Pig into Spark. What I hope is an interesting question for most of the people in this room is, in practical terms, how do we get there, right? How do we get to the point where we're running the vast majority of our jobs in Apache Spark? Because I know that long tail can really be difficult to get rid of, and hopefully our experiences with what has worked in terms of cluster settings, fixes that we've had to do, features that are required, as well as best practices are useful to all of you guys. What I'm not going to talk about, though, are the high-profile Spark features that make Spark a more attractive option to data engineers. I'm not going to come up here and say, like, you can use SQL, so of course Spark is going to win. That doesn't really help, right? We're also not going to talk about some of the performance optimizations that we would have done regardless of what execution engine we're using. So Parquet performance tuning, S3 committers and optimizations, as well as our environment for user happiness, our notebook environment. Those things are going to exist anyway, and they're not really Spark focused. So if you're interested in them, I encourage you to check out talks from Netflix online at other conferences. This is primarily going to be about our challenges and best practices. So to start off, I want to point out some changes or some differences between how Netflix deploys and runs Spark applications that I think has been really, really valuable for this move in particular, getting people onto Apache Spark. So first of all, we keep our own branch of Spark that we can add features to, we can release more often, we can take upstream fixes or those sorts of things, right? I think this is a very common practice. You see companies like Databricks or Cloudera, even large companies like, I assume, LinkedIn and you know the big ones, doing this where they have their own branch. But in order to maintain that branch, you have two options that are at really far ends of the scale, right? You have on the left-hand side, you can pull in a brand new Spark release. You can rebase and take all of those changes. And this is really great for getting huge changes that have happened in upstream Spark, like data source v2. You know, you're probably not going to backport 100 fixes or 100 patches into your Spark version. So getting it is really beneficial. On the other hand, you're pulling in everything. You're pulling in the last patch that went into that release branch that may not be 100% correct until like a couple patch releases later. And so it's also really easy to break things, pull in new features that aren't quite ready, you know, have, say, a new feature turned on by default, and it's really bad in terms of predictability for customers. On the opposite end of the spectrum, we have perfect predictability because all we change is backports. We take one patch, make sure we understand the whole thing, and apply it by hand to our Spark version, and we know that we have changed nothing else and all jobs should continue running. And the problem with that is it's really, really time consuming. It's sort of safe, but honestly, when a patch applies cleanly, we don't really take a look. No one does, right? You want to just get your backports done as quickly as possible. Hey, they say we need this. I don't understand code gen. I'm just going to ship it. So we have these two very opposite options for how to maintain branches. And what Netflix does is we sort of try to do both. So what Netflix does is we maintain parallel branches. Instead of saying that we're going to move all of our infrastructure and all of our jobs from 2.2 to 2.3 in 6 months and make this a gigantic nightmare for everyone, what we do is we periodically rebase and we grab a new Spark branch. So we currently have Spark releases for 1.6, 2.0, 2.1, 2.3, and we're targeting a 3.0 branch. Then we maintain those branches with backports. Right? Anything that looks like our users need it, anything that is not substantial changes and things like that. What this does is it gives our users as well as us, a flexibility of not having to choose a single Spark version and make sure it's exactly perfect. So we can do things like recommend a version of Spark based on actual use. If we release, say, and this is actually happening right now, we've released 2.3 in our infrastructure. No one really seems to be moving to 2.3. 2.3 has a couple of problems with, it broke the way we do stats calculations. It broke ours, it's fine out there. It works internally, but it doesn't work for Netflix. So our broadcast joins are somewhat broken. You have to manually do it. So no one's moving to 2.3 yet. So we know that, and we don't have to make 2.3 our recommended version. And what's even better, we didn't have to force anyone to move to 2.3 before it was ready, right? We want to see early adopters proving it out, telling us this has way better performance, everyone should be moving to it, make sure there are no big problems, and then move that recommended version and tell people, hey, we think it's safe. Eventually, we also want to be able to just say, our recommended version is now 2.3. We don't see any problem with that. We're going to flip a switch and automatically canary jobs over to it until we actually get everyone moved. So this, I think, has really increased the velocity of uptake on Spark because our users know they can always continue using whatever version they compiled against and not worry that we're going to force them in 2 months to change something. It just reduces a lot of friction while also allowing our data platform team to move fast and to really innovate in Spark. It's also, sorry, yes, covered that. Now, it does require, however, quite a bit of testing. So just to make sure everyone knows, like what we recommend, we have unstable branches where we will do initial backports for a customer. Say, hey, I want this higher order function from 2.4. We go and backport that feature. We say it's released in unstable. Can you go test it, make sure it works? Then while they're making sure it works, we run nightly canaries on that version to make sure that all of our important jobs, those continue to work as expected. Then we run unit tests on every single build, and we also use integration tests to validate the behavior, high-level behavior of tables for every deployment. So we're pretty aggressive in testing, and I think this has been really good for us maintaining all of these branches, because we don't really have a ton of time. So we've gone and done this. We still have all 4 of these branches available. 1.6 just had scale problems. You can't go above 500 executors. 2.0 was a little unpolished. We got a lot of new features into that release, and they weren't really fully baked until 2.1. 2.1 is our workhorse. Pretty solid, although we've backported a lot of things and really forced it to be solid. I think if you're going with upstream releases, 2.2 or 2.3 is probably a better choice. And then, like I said, 2.3 is available, but we're seeing a pretty slow migration over to it. All right. Next, I want to talk about some of the challenges that we've hit over the last 3 years and what we've done about them to share some of our, work and things that you should be looking for in a Spark version if you're going to run it. So first of all, stability in the 1.6 line was pretty bad, at least for us. I don't know what scale most people run at, but our clusters by default, our Spark applications by default are 500 executors or more. We rarely see people scale down below, although 500 maximum executors because we use dynamic allocation. We rarely see people change that below 500, just trying to be nice to other people. That never happens. So it's always 500 or more. And 1.6 simply couldn't go beyond that. It had strange locking dependencies. So 1.6 continued to use ACA and the actor model for a lot of the internal systems. Internal subsystems that are using actor model can only process one message at a time. And what we saw was a whole bunch of methods that were synchronized on the object itself. So in the method definition, it's just, hey, def, this is synchronized. So we can do whatever changes we want to inside this actor. The problem there is that that's a really coarse level to lock at. And so some of the systems that needed to be more high performance simply weren't. You could, I think the yarn allocator, for instance, just couldn't handle that many requests. So we had unstable situations caused by that. That would cause RPCs to back up. Once RPCs back up, we have retry storms, and retry storms in 1.6 were just never solved. So that was a pretty big problem. What we think has happened since is that some of these systems have fixed locking, fixed RPC calls, maybe backed off the retries and things like that. So it got better in 2.0 and a whole lot better in 2.1. But the fact is, we think that Spark really could use distributed tracing. I think that Spark is hopefully the last major processing engine to be written without distributed tracing built into its RPC framework. We just need to know exactly what RPCs are dependent on other things, where those cross process dependencies are, so that we can reason about this better and really fix those problems. We think that we're probably still haunted by the early locking model used by Spark 1.6. It's so much better in 2.1. In 2.1, we've gone up to, say, 4,000 executors in a single Spark application. We usually, at that point, really recommend people increase the number of cores in their executors as well. But 2.1 just happened to be a whole lot better. We also backported quite a few changes. So remove block status data from heartbeats. That was pretty critical to get the size of individual heartbeat messages down and stop taking up so much space and memory on the driver. That was really helpful for stability and scaling up to that point where we can get 4,000 executors. Also, the multi-threaded listener bus, which was added, I think, by Marcelo, was really fantastic. So before this, the listener bus, because of locking and the worker situation, just could not handle a lot of messages coming in. And multi-threading really helped here. And that means that the UI stays in sync with the application as it runs. It also means that the history files are able to be written at the same rate that the application progresses. So you don't have the situation where your history files and your UI are out of date and you can't tell what went on without going into the driver logs. We also fixed unstable executor requests, which was a pretty critical thing for going above, say, 1,000 executors and not having your executor counts at some point just start going unstable and fluctuating 100 up, 100 down, 100 up, 100 down, and actually causing jobs to die because there's a limit on the total number of executors you can bring up and kill, even with dynamic allocation. That said, we're still haunted by some of these things. When we get to applications with stages that run more than 100,000 tasks, Spark UI still gets out of date. We see just massive problems and basically instability. Applications can hang after shutdown. If you have aggregation, so like max length of some string across 100,000 tasks or 100,000 files, what ends up happening is it completes and you get the correct answer, and then the Spark application hangs waiting to write the history file or writing out that information to the history file, and then it eventually dies because Yarn times it out. So we think that there's still a lot more work here to do. Our primary recommendation to work around this, and this is something that we're broadcasting to our user base is increase your split size, so your max partition bytes, or use coalesce to just get that number of tasks down. We also have been lucky enough to hit all sorts of unlikely problems. Unlikely problems are things like S3 consistency errors, as well as some fun things that we'll go into. The point here, though, is that when you're at the scale that Netflix runs its clusters, unlikely problems happen all the time. We have several of these a day, and they're weird. They're really, really strange. We care about these because when an unlikely problem happens and like a job hangs as a result of it, we had output coordinator problems where a task completes or was preempted after it completed or after it was authorized, and as a result, the application just hangs because a single task can't commit, and it just retries that task over and over and over. That really decreases the confidence that our users have in Spark because it happens all the time, and because if you're running 100 jobs a day and one of them typically fails or has a problem, it's really detrimental to our platform as a whole. So we care a lot about unlikely problems. We have scale in basically every dimension that can cause problems. So we have clusters with thousands of nodes, 20 disks on each node, so we have, say, 20,000 disks in a cluster at any given time. So if there's any problem detecting a bad disk or a slow disk or something like that, it can cause really huge problems. We also have tens of thousands of executions, those Spark applications, high tens of thousands. We have jobs with thousands of executors, thousands of cores, huge numbers of tasks. I think we've seen a job running in production with 2 million tasks, which I was impressed they got that working. And we also have a really diverse set of workloads because of the data in our company. We use our big data platform for everything from financial planning to recommendations to how are our runtime systems performing at this moment. So we actually have quite a bit of different things running. So the unlikely problems we've hit, the output coordinator one I mentioned, we've also hit some really strange things with the output committers. So the output committer, we had a problem where attempt IDs were reused across stages. And if those two IDs ran on the exact same machine at the exact same time, so like different tasks from the same stage, running on the same machine at the same time because we didn't cancel all the tasks from the previous iteration of the stage, then we had a correctness bug. And that was actually really tough to track down. So we've gotten those fixes into upstream Spark. I highly recommend using like 2.4, I think had that particular fix. Especially if you write your own output committers. It's just really, really difficult to debug these things. But your users will come to you and say, hey, I'm missing 2,000 records. Where'd they go? We also have taken several actions to basically increase reliability using the generic features of our clusters. And I think these have been really important for our adoption curve. Turning off yarn preemption in production worked for us because we have so many containers in our clusters that the turnover is really large. And even if you're a super important app, our apps just don't have trouble getting containers because the turnover is so high. So turning off preemption really removed a lot of those cases where you're basically chaos monkey testing your Spark application. And that was not a very fun thing to do all the time. We also use C groups in Linux to jail applications and make sure they stay on just their cores because we had problems with noisy neighbors taking up, say, all the threads or all the cores on a box and causing really high runtimes for other applications. Also a difficult one to debug. C groups was a really critical part of our infrastructure there. We also then apply Spark's general purpose features. If you're not using a version of Spark with these, I highly recommend moving to one. So blacklisting at least when you're running applications as their own Spark cluster, their own set of executors. I've heard that this has a problem when you're sharing executors across apps. But blacklisting those executors or changing your blacklisting settings can really help so that you don't continue running the same failing task on one machine that is always going to fail. That causes application failure, and what we want to do is avoid a cascading failure because one single machine was bad. To that end, we also have speculative execution. So if a task is running slow, run it somewhere else and just race them. That was really helpful as well, particularly for just runtimes. Predictable runtimes also really help that adoption curve. Users want to know that not only is their job going to complete successfully, but it'll complete in about the same amount of time every time. And the last thing is adaptive execution. We turn on adaptive execution by default, and this has been really helpful for us because, number one, it allows you to see when you only have like 2 keys in a join. You don't run 10,000 tasks and 2 of them run really, really slow. You can see you only get 2 tasks because only 2 tasks had data. So debugging jobs at a user level was made really easy by adaptive execution. And adaptive execution also reduces the footprint, the executor footprint of certain stages across your cluster. So if you have bad nodes, you want to keep that footprint down. It's going to reduce the likelihood that you hit a bad node. The last main challenge that we've hit is pretty much memory management. We have OOM issues, and the really painful ones aren't necessarily executor OOM issues, but driver out-of-memory issues. And there are 3 main causes of driver out-of-memory issues. The first is broadcast joins. The second is collect. And the third is user doing something crazy in their job. So building a gigantic broadcast table on their own because they think they can do it better than Spark can. We've definitely seen that. Collecting in order to build that crazy table, we've seen that. And so we've addressed this in several different ways. First of all, Spark 22170, basically we need to take a closer look at how Spark builds these broadcast tables. What Spark was doing was running a stage, pulling all of those compressed blocks back to the driver, decompressing all of the data into rows, building a broadcast table out of those rows, and then copying that into a buffer for serialization. So we were copying the exact same table data like 4 times. And that was really expensive. So 22170 basically just said, once we've pulled back all of those compressed blocks, iterate through the compressed blocks to build our broadcast table. So getting rid of essentially 1 copy of the entire broadcast table in driver memory, that was really helpful for us. But there are a lot of ways where we can improve, maybe pull back 1 block at a time. Again, the collect operation that broadcasts use is really expensive, and it shouldn't be. We should just iterate through blocks. Another thing that we did was we added PySpark memory regions, and the best one was basing stats on row count and not size on disk. So we use a lot of Parquet. Parquet can get great compression, but the compression in Parquet does not reflect the amount of space it's going to take up in Spark memory. Space it takes up in Spark memory is what really matters when you're building a broadcast table. So basing stats on row count meant that Spark doesn't make the wrong decision about whether or not to broadcast a table all the time. So that was super helpful. The other thing that we've done is that we've just tried to educate our users about memory management and memory issues. There's a lot we can do at the Spark level, but users understanding what memory regions they have and how to use those memory regions or what could go wrong is really, really helpful for us. This was probably like the biggest impactful thing I did in 2018, just documenting Spark's memory layout. And our users found it incredibly useful because it allowed them to understand things like, when my job is running slow and I have more spill, right, what memory region is that using? How do I increase the allocation to just that memory region to affect the problem that I'm having? What they were doing before was, say they had their own big broadcast variable, like a try, to do like IP address lookups or something. If you build your own broadcast variable, that doesn't live in Spark memory. But increasing spark.executor.memory increases the memory of the JVM, and then we multiply that by a fraction to get Spark memory. And in our cluster, at the time, I think that was 70%. So when they needed room in memory for their try and increased Spark memory, 70% of that allocation was actually just going to Spark and not really helping them. So their shuffles were getting super fast because they weren't spilling to disk, but they were still running out of memory, right? So we would see these allocations just going well above what they actually needed. So educating users about the memory regions was super helpful. And at that point, we thought, we really have to put together some best practices because educating users was far more valuable than just taking and tackling these problems on our own. So the first things that we start with in terms of our best practices are, number one, avoid RDDs. I think this is pretty obvious. That's why I didn't make it its own slide. Don't use RDDs because you're probably not going to be as smart as Spark is, and they're actually really, really expensive to serialize. So cryo problems plagued our 1.6 apps, and the optimizer can't do anything about it. So just stay in data frame or SQL land. Also, aggressively broadcast your data. It just really helps. It deals with skew. It helps in a number of ways. Definitely do it. Configuration best practice. So assuming that your data platform team has reasonable defaults for your environment, don't copy configuration, and don't change it if you don't know what it does. Those two things, we would have people, like, I think I told one person when they had a really, really wide data frame, turn off code gen, whole stage code gen, because you can't turn off code gen. Turn off whole stage code gen. And then I saw it popping up just like everywhere. Like, why are you turning off whole stage code gen? Oh, well, we heard it affects stability. Don't copy settings. And we actually documented a section in our documentation. We say, these are the settings that if you want to touch these, go talk to data platform because we can help you understand whether or not you need them. So it's really that user outreach and that two-way conversation. The last thing is never change timeouts, because timeouts just hide problems. We can make the timeout 20 minutes or 2 hours or whatever, but the underlying problem with your application is still there. It's just that it takes an extra 2 hours to fail, or that you still have that problem and the bug is lurking for the next time your data size increases. So we definitely don't have them change timeouts. Unfortunately, we also still have to have users know how to control their SQL parallelism. This is really tough. I would love it if Spark were smarter here. Adaptive execution is one step in the right direction, but we are not there yet. So know how to control parallelism. If you're creating more than 100,000 tasks, get that parallelism down. We want low tens of thousands, because no matter what you do, Spark really can't handle that many. Also know repartition versus coalesce. Repartitioning your data can deal with the underlying skew. So if you have a skewed broadcast join, that is a time when you need to repartition your data to spread out those records that are really hitting in that join. We also encourage our users to just don't touch it if it's not doing anything bad. So use the least intrusive option. Maybe you set your shuffle parallelism high and turn on adaptive execution. But we want to get out of Spark's way, because platforms should be bringing in new Spark versions and building things that make your jobs automatically faster. We want to rely on Spark, rely on the optimizer, so that we're not in a situation like we were with Pig, where every single one of our jobs had to be hand-tuned. The next one we've covered actually several times now, avoid wide stages. Spark really doesn't do well above 100,000 tasks. You can lose driver heartbeats, jobs can hang, and also the one that we haven't covered on this slide is what happens to shuffles. So the number of shards in a shuffle is approximately, depending on data skew, the number of map tasks or inputs to that shuffle times the number of outputs or reduced tasks in that shuffle. And so if you have a job with 40,000 read tasks, then, and I don't know, 1,000 reducers, then you're really like at, what, 4 million tasks? Shards of data that have to be pulled across the network. That's a lot of connections, that's a lot of problems. So we really encourage users to be aware of that and keep all stages of their jobs down. We also, we use dynamic allocation. So one of the first things that we had to fix was accidentally specifying num executors was causing you to use static allocation, which users almost never want. The only time users want static allocation, they actually want some minimum cluster size for caching or something like that. And in that case, they need to use min executors. They don't want to prevent their job from scaling up. They just want to prevent it from scaling down. This also means that we have to materialize data instead of caching it, because caching is really expensive, causes your executors to stay around for a longer period of time. So we encourage people to, well, we actually built a materialize call that we need to push upstream, but it converts to RDD, converts back to data frame, and then runs a count operation. And what happens there is it puts all of the data, like it executes some query up to a certain point, puts all that data in the shuffle system. So we can resume from that point, but we don't have to keep executors around to do it. Ooh, I am about out of time. Last one is sort before writing, and this is probably my favorite. Always add a sort before you write your data, by partition columns, filter columns, and then one high cardinality column. And the reason why we do that, there are just a ton of reasons, actually. Like, jobs just go more smoothly. So first of all, if you add your partition columns first, you're going to cluster your data by partition. And that way, when you write out, you're going to get a minimum number of files in that output table. Files, this avoids the small files problem. It really, really helps. Next, you're going to cluster your data by common filter columns. So if you're using something like Parquet, where you can actually filter row groups and entire files based on the metadata of those columns, this is going to make you ignore a whole lot more data. Instead of taking some key that you're looking for and putting it in every file in a partition, you cluster it together and put it in just 2 files in that partition, and that way you can read just those 2 files. The next, and this is why you need a high cardinality column at the end of your order by, Spark can add, or Spark, when you order by, does a skew estimation step. So Spark will go run the stage, figure out what the skew looks like, and then divide that up into approximately equal-sized tasks based on the number of records. That's really, really helpful because if you have any skew in your output data, that's going to cause your job to take a really long time. The most expensive part is preparing that data for output and actually writing to the file system. So if you take care of skew first and just take care of skew by default, then you don't have to worry about, hey, why is this taking an hour now because my data size doubled. All right. I was going to go into where we're at now and what's next, but we have 30 seconds left. So I think I've mentioned a lot of what we can do. I only had 3 slides, it's fine. I've mentioned a lot of what we can do in Spark already, and that was really what I wanted to get across in those last slides. We really need to improve memory management, and I'm super excited about Data Source v2. With that, thank you all for coming, and I'll be, I guess, out there or probably maybe here for questions. I don't know what the situation is like, because now it's lunch.
Yeah.
Thank you.
We'll be available in the back of the room.